Our examples so far have been of linear differential equations. What about nonlinear differential equations? Those tend to be pretty difficult. Let's see what series expansion can do in this case. Let's do an example that points back to something we've done in the past. Consider the differential equation dx dt equals x squared. Let's say that we have a simple initial condition. At time 0, x is equal to 1. Now, we've done a more general version of this equation in the past, where dx dt is alpha times x squared. And we got the general solution to that. Do you remember? X as a function of t was 1 over the inverse of the initial condition minus alpha times t. And that had a blow up. It was really kind of cool. So what's the solution in this case? Well, in this case, we know exactly what it is. X of t is 1 over 1 minus t. Now, why is that? Oh, wait, go back to that more general case. Now, alpha is equal to 1. The initial condition is equal to 1. Yep, that's it. That's our solution. So we already know what the answer is. And I recognize that. I know what the series expansion for that is. That's just the geometric series. So this is going to be really easy, right? Well, let's see. Remember the way this works. We take x and we expand it out as the sum, k goes from 0 to infinity, of ck times t to the k. Then we take the derivative. We remember what that is. After reindexing, you got the sum, 0 to infinity, l plus 1 times cl plus 1 t to the l. We're using that different index thing, just as usual. If we expand out what x is, I can write it as 1 plus c1t plus c2t squared plus c3t cubed. Keep going, keep going. Wait a minute. How do I know that that first term is a 1? Isn't that supposed to be c naught? Well, yes, but we already know that the initial condition is 1. So plug in t equals 0. All the terms vanish except for that degree 0 term. Okay, so that's our x. Now, all we need to do is square it. Then set it equal to the derivative. So, what's x squared? This is going to be like some long polynomial multiplication thing, right? First outside, inside, last kind of thing. I do know that the degree 0 term is 1 times 1, which is 1. That's not so bad. What about the degree 1 term? Well, let's see. That's things with a t. That's 1 times c1 plus c1 times 1. That's going to be 2c1 times t. Okay, also not so bad. Now, the t squared term. Would you believe me if I told you that the coefficient in front of that was c1 squared plus 2 times c2? Maybe you do, maybe you don't. Check it, find out. And then you just keep going, and then it's not going to be so bad, right? It'll be some kind of pattern. We just need to square it. Let's keep going. I'm going to save you a little bit of work, tell you that the next term in this series is going to be 2 times quantity c1, c2 plus c3, all of that times t cubed. That looks a little funny. What about the fourth order term? That is going to be quantity 2c1, c3 plus c2 squared plus 2c4. All of that times t to the fourth. Whew, wow. Now, in the end, what we're going to do is set that equal to dx dt. Writing that out term by term, we know what that is. That's c1 plus 2c2 times t plus 3c3 times t squared plus 4c4 times t cubed. You keep going with that. Now, with what we've got so far, this seems like it's not so bad. If I equate the terms degree by degree, then in degree 0, I get that 1 is equal to c1. That's great. Perfect. In degree 1, what do I get? Match up the coefficients in front of the t's. I get 2c1 equals 2c2. That means c2 is equal to c1, but I already know c1 is equal to 1. So that's it. We get that c2 equals 1 as well. Fantastic. Equate the coefficients of the quadratic terms, and we get that c3 is equal to 1. Well, you got to check that. It's like c1 squared plus 2c2 all divided by 3. Ah, boy, there's some algebra in there. And then keep going. And then keep going. And I'm afraid these equations seem to get more and more complicated. But we're not giving up. No, we just need to keep going. We just need to square it. We just need to square it.
We just need to square it.
And this is where the problem lies. And it's massively frustrating because in this case, we already know what the answer is going to be, right? We already know that the solution is 1 over 1 minus t. We already know that the geometric series says that x has to be 1 plus t squared plus t cubed plus t to the fourth, keep going. And we know that all of those coefficients have to be equal to 1. But showing it, proving it, well, is it possible? Yes, it's possible. But it's not easy, and it's not obvious at all. In general, this method, using series for nonlinear differential equations, it quickly gets algebraically super difficult. And this was a simple example, one where we already knew the answer. There are much more challenging examples out there where, oh boy, I feel like giving up. Are you feeling stressed out? You should relax. This whole chapter on series for ODEs, it's kind of a side quest. It's not really part of the main storyline that we're talking about. These series methods, they're cool, but they're hard. And to be honest, they're a little bit niche. So I hope you enjoyed our exploration of it. It's nice to connect back to series, but in the end, these methods aren't going to be massively important to what we're doing here on out.